In this video, we'll be talking about odds and expectation. And our goal here is to just learn how to compute expected value. So, expected value or also referred to as just expectation is used to determine the result that would be expected over the long term in some sort of gamble. It is used not only for games of chance, but in areas like insurance, management, engineering, and others. The idea is to try to figure out the long-term expectation if some experiment is repeated numerous times. But here's the key to remember as we study expected value. It only makes sense for events that have numerical outcomes. For example, rolling a die has a numerical outcome, 1 through 6, and expected value can be used to determine what the average long-run result is likely to be, which we will look at in example 2. But it doesn't make sense to ask what the long-term average of flipping a coin is because you can't average heads and tails. So let's dive into our first example where we develop a procedure for finding expected value. So let's consider a scenario. Let's say that you pay $1 to roll 2 dice. If you roll a total of 5 or 6, you get your $1 back, plus 2 more just like it. If not, you're getting nothing. Okay? So we want to find the probability of winning the game first, and then if we play the game 100 times on average, we want to figure out how many times would you expect to win, and then what would be the total amount won or lost. So let's take these one at a time. Back in section 10.4, we looked at the experiment of rolling a dice 2 times, and we developed the sample space for that. If you don't remember, you might go back and revisit the video from section 10.4, where we went over an example where we developed that sample space, and we found out that there were 36 possible outcomes when you roll a dice twice, and of those 36 outcomes, there are 9 of them that result in either a 5 or a 6. Okay, so we would say probability of getting a 5 or a 6 is equal to 9 out of 36, and this reduces down to 1/4. Okay, so the probability of winning this game is 1 out of 4, 1/4. Okay. If you play the game 100 times, on average, how many times would you expect to win? Well, since you have a 1 out of 4 chance of winning any game, on average, if you played 100 games, you'd expect to win 1 out of 4 of those, right? Or 25. You'd expect to win 25 out of every 100 games. Okay, that does not mean that every time you play the game 100 times, you win exactly 25 of those times, but it means on average, right, that you would expect to win about 25 games out of every 100 games. Okay? What would be the total amount won or lost? Well, according to the description of the game, if you lose, you don't get your $1 back. You lose $1, right? You have to pay $1 to play the game, and every time you lose, you're out your $1, right? If you win, you get a total of you get your $1 back plus 2 more just like it, right? So you come out ahead by $2 if you win, right? So it would look like this. If you win, you come out ahead by $2, right? So you would expect to be about 25 wins and about 75 losses. And when you lose, you're out $1, right? So this works out to be $50 minus $75, which equals negative $25. Okay. So if you play the game 100 times, you'd expect to lose, on average, $25. Okay? So this is what we would call the expected value of playing the game 100 times. You would expect to lose $25 on average. Okay? Now, in example 1, we saw that playing a dice game 100 times would result in a loss of $25 on average. That means that every time we play the game once, we can expect to lose 25 cents. That might not make sense to you at first, since you can't possibly lose 25 cents playing the game once. You either win $2 or you lose $1, but that's the point of expected value. It's about what the result of a probability experiment would be on average. Okay? It doesn't tell us what will happen on any given trial. It's saying that if we play this game a whole bunch of times, we would expect, on average, to lose about 25 cents every time we played. Okay? In any case, a close look at example 1 allows us to develop a general procedure for finding expected value. We first found the probability of each outcome. Then we multiplied each probability by the numeric value of the outcome and added the results to get the expected value. So we can use that to come up with a formula for expected value. The expected value for the outcomes of a probability experiment is given by this formula right here. Expected value equals x1 times p of x1 plus x2 times p of x2 plus x sub n times p of x sub n, where the x's correspond to the numerical outcomes of the experiment, and the p of x's are the corresponding probabilities of the outcomes. So we take each possible outcome and multiply it by its probability, and we do that for all the possible outcomes and add those products together. Let's look at another example. When a single die is rolled, find the expected value of the outcome and describe what exactly that means. Since each numerical outcome 1 through 6 has a probability of 1/6, the expected value, using this formula right here, would look like this. Expected value, so we've got the outcome of rolling a 1 times its probability of 1/6, plus the outcome of rolling a 2 times its probability of 1/6, right? And so on. Outcome of rolling a 3 times its probability of 1/6. We do this for all the possible outcomes. Okay, like so. This works out to be like 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. 3, 6, 10, 15. If you work this out and put it into decimal form, it actually works out to be 3.5. Okay? That doesn't mean that you would get a 3.5 if you roll the die one time, right? Because obviously if you roll the die, anytime you roll the die, you're going to get one of the specific numbers 1 through 6. But what this is saying is that if you roll the die a whole bunch of times, the average of all the outcomes should approach or kind of average out to the long-term average would be 3.5. Okay. In gambling games, the expected value is found by multiplying the amount won, or net gain, and the amount lost by the corresponding probabilities, and then finding the sum. Let's explore a couple of examples using this idea. Example 3. Computing an expected value. The prize in a raffle is a flat-screen TV valued at $350, and 1,000 tickets are sold. What is the expected value if you buy one ticket? Okay. Okay. All right, so it doesn't specify here, but we're assuming that the price of the raffle ticket is $1, okay? So for the expected value, we need to, first of all, figure out the probability of winning, and that would be 1 out of 1,000. And we multiply that probability by the amount won. The amount won is not $350, but it's actually $349, right? Because you had to pay $1 to play the game. So you come out ahead by $349 if you win. I add to that the probability of losing. And the probability of losing is there is 999 losing tickets, right, out of 1,000. And if you lose, you're just out $1, right? Because that's the cost of buying a raffle ticket. Okay. So this is equal to 349 over 1,000 minus 999 out of 1,000. If you put this in a decimal, a dollar amount, it works out to be negative 65 cents. Okay. So you do not expect to come out ahead if you buy a raffle ticket, if you participate in this game, right? You might get lucky and buy that one winning ticket, but if you participate in this game many times, over the long run, you would expect to lose 65 cents every time you play this game, every time you basically buy a raffle ticket. That's kind of your long-term expected result. Let's look at another example. Let's say that 1,000 tickets are sold at $1 each for 4 prizes of $100, $50, $25, and $10. What is the expected value if you buy 2 tickets? Let's begin by finding the expected value for just buying 1 ticket. Okay. So I got to I've got to add 4 values together, corresponding to each of the 4 prizes, right? So the probabilities of winning each of the 4 prizes is the same, right? Because there's 1,000 tickets and 1 ticket corresponding to each prize, right? So the probability of winning the $100 is 1 out of 1,000. If you win the $100, you don't actually get to keep $100. You get to keep $99 because you have to pay $1 to buy a ticket, right? Probability of winning the $50 prize is also 1 out of 1,000, but you actually only get to keep $49, right? Again, because you have to buy the ticket. The probability of winning the $25 prize is 1 out of 1,000. You get to keep $24 for that. And the probability of winning the $10 prize is 1 out of 1,000. And you get to keep $9 for that. And then, sorry, I'm running out of space, but coming down here, I have to also put in here the probability of not winning any of the prizes. And that would be 996 out of 1,000. And if that happens, you just lose $1, right? The price of the ticket. So if you work this out using your calculator, it comes out to be about negative 0.815. Okay, so an expected loss of about 82 cents every time you play the game, every time you buy a ticket. So if you want to find your expected value of buying 2 tickets, you would multiply this result by 2. Okay, expected value for 2 tickets. This would be negative 0.815 times 2, which is negative $1.63. Okay, so that would be your expected value if you bought 2 tickets in this game. So that's the idea behind expected value. This is a short little section. But again, the idea of the expected value, it is the long-term average expected result if you perform an experiment numerous times. And again, it only applies for experiments that have a numerical outcome, right? Because we're talking about the long-term average. of an experiment that has a numerical outcome. So that's it for this video. We'll just wrap this up here. Thank you for watching.